Hello guys, welcome back to my channel Gamma Digamma. So in this video, I would like to continue with my complex analysis series. The last time we did the Cauchy-goursat theorem. Now we're gonna do the Cauchy integral formula. So please check out the previous video if you haven't already, because the ideas are pretty derivative. Let's get started. Okay, so before jumping into today's main discussion, I would like to make you guys comfortable with a certain idea, a certain concept, and that is contour deformation. Okay, so assume you have a line like this. I mean, not really like a closed loop or a real contour. It's called C0, and you have another one which is like a semicircular closed loop. But you know, this direction is important. That's the direction you're integrating on. And okay, so here I've shown like there's this gap here, but I want to emphasize that this gap is negligible. It's like they're basically touching each other. I can't show this here because I want to prove a point. So now I take a complex function z, w of z. I integrate that over C0, and I add that with the integration along this contour in the direction denoted. So if you say this is C, and that is equal to, now what happens when you do stuff like this is you get this, and since there's like literally like zero gap between them, so the contribution of this guy was in this right hand direction, this was a left hand direction, literally along the same path, integrating the same function. These guys are gonna mutually cancel each other out, so we have a gap because the contours the integrations cancelled out, the top part because that didn't cancel out, and then the other part. And you can call this entire structure, this dotted line isn't really there, just showing what was removed. You can call this C1. So that is equal to integral over C1. So that's the idea of contour deformation, that if like the contributions are similar, if you're integrating the same function over similar path in opposite directions, you're going to cancel it out, and if they're in the same direction, you're going to add them. So it's going to be probably like 2 times the function on one path. So it's this idea of like cancelling contributions out. This you can say that this is like one version of contour deformation. The other version that's useful is if you remember like some Stokes law back in vector calculus. It was, so you had a vector function f, so the closed loop integral of line integral, and that was equal to the surface area enclosed, I don't know, of the curl of f. Now, what area enclosed should we take? If you have some closed loop like this, what area enclosed should we take? We usually we can take any area that has this as its boundary. So you might say, well, why not take like this, like bulging spheroidal cap or something? But if you want to integrate, if you want to use Stokes theorem like this, you're on your own. I don't want to parameterize over this crazy surface. So what you do is, see, the idea is, as long as you have the same boundary, integration over this shaded blob which has a boundary of the same closed loop, can be deformed keeping the boundary same again. The boundary should be same, otherwise it's going to be some other integral of this area, this flat area of the area, the circular area inside it. And believe me, the area of a circle is much easy to calculate in, it's probably like an exercise in some basic calculus. So this is how you can like modify these areas keeping the boundary same, then you're going to get the same integral. So it's about choosing the convenient area with the same boundary. So the idea we're going to use later in this video is sort of like tying both of these concepts together. Okay, so let's move on with what we have to do. Okay, consider the complex valued function w of z, which can be represented as f of z over z minus z naught. And z naught is some point that belongs in the complex plane. Now, consider a contour C1. Like z naught's like outside here somewhere. Well, on this region C1, the region that's enclosed, C1's the contour, like the region enclosed in C1, the functions w of z is going to be analytic everywhere, because f of z is analytic in its own right. It's not going to contribute to any poles. And the denominator also won't reach 0 because z naught is outside the contour or outside this region. Hence, on this region C1, we have f of z over z minus z naught. Let me point out that f of z is analytic. Well, the value is going to be of this integral is going to be 0 by Cauchy-goursat theorem, because there's no poles here. There's no places where the entire function is going to blow up anywhere. Z naught's outside. F of z doesn't blow up in its own way. Hence, it's all going to be 0. And watch the previous video if you don't know what I'm talking about. It was proved in the previous video. Now, let's consider a more interesting case and a more general, weird shaped contour. So you have like a contour like this, going this way. And now z naught is inside the region enclosed by this contour. Call this C2, and z naught's like inside somewhere. Now the problem is you can't use this. You can't use this, because now the entire function w of z is not analytic inside. The denominator will blow up to infinity, making this entire function non-analytic in this region. So what do we do? I mean, I'm sure you might have guessed by now. Contour deformation. How do we deform this? Now, this is a very clever technique, extremely important in complex analysis. I think we do it a couple of times. So, okay, assume this is the same contour as before, like z naught's over here somewhere. What you're gonna do is you have this path, like the external path is like as it is. You're gonna like go in the contour and like loop over z naught, like sort of exclude z naught. And I'm just gonna denote the direction here. And this gap between these guys, call that r. That r goes to 0, so that when this gap actually goes to 0, you just basically get this back, because like the contribution of this guy and this guy will cancel out, essentially giving nothing, like no contour line there. And I want to make the radius of this inner circle. So if you notice this circle here, if I make the distance between this outer going and inner going segment 0, you're going to get a complete circle. There's not going to be an open space in the circle. So circle is going to look like this. And I made a circle because circles are easiest to parameterize. You're going to get a closed circle like this, and I want the radius of this circle, call this epsilon. I want the radius of this circle to go to 0. because we didn't have a circle in here, right? We're introducing these things, so these things have to go to 0. Otherwise, you're working on a different contour, doing a different integration. So this is C2 deformed. Let me probably do a better job of drawing it. So all I'm saying is you have this, and then this circle, and this. Directions like this. And there's an inner circle in here, like the perfect circle. I mean, we were free to choose any shape inside. We're choosing a circle because those are the best to work with. And this circle has a radius epsilon, which goes to 0 because we're introducing it, and the gap between those two segments, or the r, also goes to 0. And so that these two guys, the contribution mutually cancels out, giving us the original contour basically. Now let's integrate over this. We have integral over C2 entirely, f of z over z minus z naught dz, is equal to, we have I don't know, where should we start from? We can start from here. So this outer integral, call the outer guy alpha, the inner guy beta, and so this guy, outgoing segment is gamma 1, ingoing segment is gamma 2. So we have integral over alpha, f of z over z minus z naught dz. Then we reach this point. Then we have integral over gamma 2, f of z over z minus z naught dz. Then we have integral over beta now, f of z over z minus z naught dz, and then integral over gamma 1, f of z over z minus z naught dz. Now, as I said, as the difference between the the difference between these paths, distance between these paths goes to 0, both of these integrals are going to cancel out because the contributions will be 0. That was the entire essence of using contour deformation like this. And you have just integral over alpha basically. I think I should call this C2 prime because that's the deformed contour. But now notice that in this guy, this external. Okay, now let me just shade this region basically. In this shaded region, you're excluding z naught, right? Because z naught's outside this, this weird stuff, including the circle is this new boundary. Z naught's outside that, so we can use Cauchy-goursat on that, and we get 0. And also remark one thing, that alpha is going this way, which is anti-clockwise, and beta is going this way, which is clockwise. Hence this clockwise direction has to be negative, and this entire equation is equal to 0 by Cauchy-goursat, because z naught is not in there. Its function is completely analytic over this shaded part. You can apply Cauchy-goursat. So you just have integral over alpha, f of z over z minus z naught dz is simply equal to integral over beta, f of z over z minus z naught. Now let's parameterize this integral over beta. It's a circle centered at z naught. So we have z naught plus radius is epsilon, as I said, e to the I theta, and theta is going to go from 0 to 2 pi, complete circle. So dz just becomes epsilon I e to the I theta d theta. We just have integral over alpha, f of z z minus z naught dz is equal to let's see, integral from 0 to 2 pi. Let me take the limit as epsilon goes to 0, because that was a condition for contour deformation. We need epsilon to go to 0, remember? Otherwise this wouldn't work. It's integral from 0 to 2 pi. F of z naught plus epsilon e to the I theta over epsilon e to the I theta, epsilon I e to the I theta d theta. So epsilon cancels out, e cancels out. We have I times, well, by using some continuity and convergence we can take the limit inside. Epsilon goes to 0, f of z naught plus epsilon e to the I theta d theta, and that is just going to be I times integral from 0 to 2 pi f of z naught, because this can go to 0, d theta. Well, f of z naught is a constant, you know, if f evaluated at z naught, which is a specific point, it can come out of the integral from 0 to 2 pi d theta 2 pi. That's equal to integral over alpha f of z over z minus z naught dz. Now notice what happens to, what is alpha actually after contour deformation. Well, this gap is 0 and this circle 0, so this entire middle region pretty much doesn't exist after, you know, applying contour deformation on alpha. So alpha, after, you know, taking the limit and bridging the gap between these two guys, just simply becomes your original contour, which was C2, basically the undeformed contour C2, f of z over z minus z naught dz. And what you can do is you can just simply isolate f of z naught. I think f of z naught just simply becomes 1 over 2 pi I contour integral over C2 f of z over z minus z naught dz. So that is your famous Cauchy integral formula. It says the contour integral over a region where, you know, w of z is non-analytic, or it has one pole at z naught. That's basically the number in the denominator. It's just going to be like 2 pi I times like f of z naught, or f of z naught is just going to be 1 over 2 pi I times contour integral over the region that contains the pole of the denominator, the z naught. Okay, I hope I didn't confuse you with all this contour deformation. What I wanted to do is, we had this original problem. We couldn't use cauchy-goursat. We did some contour deformation. We went in, circled around, came out, and went over the boundary and bridged the gap, so that, you know, and also made the circle, the radius of the circle shrink to 0, such that, you know, it's almost like we never introduced this inlet, circle, and outlet. So that after all this deformation, we end up with C2 again. And another advantage of deforming, like I think the most significant advantage is, like, we could jump over Z naught. That's why we circled over Z naught, because then we just cared about this shaded region over here, and we could apply Cauchy-goursat in this shaded region, because there was no literal pole for W of Z. This shaded region does not have Z naught anymore, so just use Cauchy-goursat. And then, you know, bridging the gaps, taking the limits, you just got C2 for this integral alpha. And I think some extra steps. If you differentiate with respect to Z naught, for example, I don't know, let's just do it. It's a crazy idea, but let's just do it. You have 1 over 2 pi I integral contour integral over C2 f of z over z minus z naught squared dz. And you can generalize this to an nth derivative. And you have n factorial 2 pi I contour integral over C2 f of z over z minus z naught raised to the power n dz. So I mean these are consequences of the Cauchy integral formula, and I think we're going to find this particularly useful later when we talk about Taylor series and Laurent series. Okay, so I hope you enjoyed this video. I hope I didn't confuse you. I hope we can work in the future to implement this idea of contour integration for bigger problems. Please like and subscribe to my channel, guys. We're just a little away from 500 subs. I would appreciate if we reach there earliest. And in the meantime, stay home, stay safe, keep doing math, stay tuned for more content. Peace out.